Okay, hi everyone. We are going to do a design review of some discrete computation for version 13 of Wolfram language. All right, let's see roughly what we have to talk about here. This is, oh my gosh, there's a lot of stuff here.
Yeah, it's going to take us a few rounds.
Okay.
So it's a lot of content this time.
All right, let's look. Well, that's good. That's done. That's not bad. Okay, graph isomorphism.
Right.
Is that a new algorithm or what?
But I mean, so the subgraph part is a new set of functions. The isomorphism part is performance.
Okay.
New libraries, new algorithms.
Find subgraph isomorphism. That's the mapping. I mean, do we have a find graph isom? Or we do here. Did we have a find graph isomorphism before?
Yes.
Which shows the actual mapping.
Yes.
Of the permutation, basically. I mean, find graph isomorphism returns a permutation, basically.
It returns a list of rules. But yeah.
Well, an association.
Okay.
Where what find graph? Excuse me. Oh, it is now an association. So wait a minute. This, when it says find graph isomorphism, it's finding all isomorphisms. Is that correct? Oh, I see. It's some number of isomorphisms. When is this function from? Why haven't I used this function? Oh my God.
2010.
All right. Okay. I could have used this function for all kinds of things. Why did I not pay attention to this function? Because we have for hypergraphs, we have some isomorphism finders like this. Okay, what's new? Is there new functionality, or is this just new performance for all these things?
Subgraph isomorphism is new functionality.
Okay. So how much, I mean, eventually we need to do graph rewriting, and we have all kinds of code from the physics project for graph rewriting. And I mean, I don't know. Okay, I mean, subgraph isomorphism is very close to graph rewriting, obviously. Right, guys?
It's one piece, yes. What key piece?
Right. I mean, then there's all this whole double push out nonsense. Okay. Find isomorphic subgraph. Find. I see. Wait a minute. Find isomorphic subgraph. I see. Returns the actual subgraph with the labels, so you can actually highlight that subgraph, for example.
Yes.
Okay. How much better is isomorphic find isomorphic graph queue? Did it get much faster?
Yeah, we significantly faster, especially in the range. I mean, it's not yet in the prototype build, we put it, but especially in the large range of 10,000 and higher, where actually right now we can't. Well, it's we will take more.
This is a new library, right?
Mixed code. It's a mixed code of that. But still based on the base Noti, right?
I thought there was a new approach other than Naughty.
Well, it's pretty much it's pretty much the same thing, but it's just different type of implementation.
I see. Okay. Look, on graph rewriting, we probably should have a session with the folks involved with the physics project who worked on graph rewriting. To nail what the design should be and so on, because we've done a lot of thinking about that. Make sense?
Yep.
Because with subgraph isomorphism, you're basically there in terms of the algorithmically difficult part of graph rewriting. Okay. Question from Ethan on our live stream. What about progress monitoring for some of these things? Is it relevant, or are they fast enough that we don't need it, or what?
I mean, you can always take an infinite amount of time, but I don't think we really want to put the effort of putting a progress monitoring here.
But I mean, if graph isomorphism is going to work, is it going to work fast, or is there a case where graph isomorphism works, but it's really slow?
Well, I look at it in terms of complexity in terms of the number of vertices, for example. So up to range of 10,000 or 100,000 is still in a decent second and such. So
you said 10 seconds at 10,000?
It should be in the range of a second. I mean, in that range of a 10 second or less with the new implementation.
Okay.
And I guess the other question is, if it's using some library, then it might not be very easy to add progress monitoring, right? If it's just spending its time inside some library function.
I mean, even normally, even if you are not using, I mean, doing the progress monitoring is costly. It will actually make the whole implementation slower, right? In a way.
Presumably. Parallelization. I don't think that's relevant. These algorithms are not readily parallelizable. I mean, if we're doing, searching a graph from this, database of graphs, so to speak. By the way, well, this is probably a wrong meeting for that, but don't you think we should have a parallel select?
Yeah. I mean, this thing of having parallel versions of everything, I think we should.
Well, maybe it should be like a headdress or something instead of having 75 functions.
Yeah, absolutely, Chris. I mean, yes.
Yeah, but also I think the reason why parallel select is a bit different is that with things like parallel map, parallel table, if the result for element 72 comes in, before the result for element 70, you know where to insert it, right? But you don't for select because you don't know how long it's going to be.
Right.
That makes sense.
That's true.
No, I mean, it has to be a bag of some kind that it puts things into. Can somebody add that to the presumably ILD agenda to talk about parallel select? I've needed it a zillion times, and what I end up having to do is some weird, mess with parallel table and then picks and things like that.
I'll pass it along to
that's
ILD.
what I typically do.
So you do select for each subtable or sub?
No, what I'm doing is I do parallel table or parallel map, get a bunch of trues and falses, and then do a pick. Right, use pick to pick from the original list.
But how do you get it parallel?
Because the parallel map is parallel. In other words, if the operation that is doing the selection test is expensive, then I'm doing that in parallel.
Oh, now I get it. Okay, that's the way you split. Okay.
But I would like to do it without ever generating all of those, in the case where I have a very large number of cases to look at, I don't want to have to regenerate all those cases.
Right.
Okay. Anything else we need to know about these ones here? So I'm assuming that molecules, I don't think we have a representative of the molecule team here, but this question about molecules as graphs and how easily you can take a molecule object and do graph operations on it. Can you?
Yeah. If you do graph of a molecule, you get a graph, among other things.
It just has a constructor. I mean, is where we limit ourselves. So, if you take a molecule, you ask the graph, we will return you the graph, but we limit ourselves there. We don't manipulate molecule in the whole framework.
Wait a minute. So if I say molecule, caffeine or something, and then I say, and then you're saying if I say this and then I say graph of that, no, that didn't work. Is that new in 13?
Yeah.
Well,
Okay.
yep, it should work.
Okay, hold on. Let me just see. That was I'm running in 12. Yeah.
That would explain it.
Yeah. Okay. Fine. Okay. You made it sound like this was a well-known thing, and I
No,
think we
no,
talked
we
about it.
pushed through a bunch of things now.
Okay. All right. I know that we talked about that recently.
Yeah, you see that like graph extensions down there? It says graph updated, construct graph objects from molecules, tree, etc.
Okay. Oh, there we go. Cool. Now, why is that? See, I think we talked about this before. I think that should use the coordinates. I don't see any reason not to use the coordinates that you get from molecule plots. And I really think we should. You see what I'm saying?
Mhm.
Charles, any objection to that? Charles?
Well, we'll try. There's probably a reason why it was not done, so we'll think about it.
I think it just wasn't thought of.
Wait a minute. Oh, no,
Ish.
sorry. Yeah.
I just put a bunch of hydrogens in there.
Yeah, no, I was just nothing.
Well, there is a question about the 3D coordinates versus the 2D.
Oh, right.
What?
No, I just remember why, because the new implementation, we are using the code from JSON. Or the original implementation, we actually generate with the coordinate.
Okay. Well,
so we preserve the embedding pretty much.
Right. So I'm saying preserve the 2D embedding. I mean, you could in
Yes.
principle preserve the 3D embedding, but I think that will be a mistake. I think you should preserve this diagrammatic embedding. What about the
Right.
double bonds? Why are those not showing up as double edges?
That's
That's an annotation. Oh,
Should
that's right. We
they?
discussed it with the chemistry
Right.
people. No, they shouldn't.
Yep.
Never mind. They shouldn't. I mean, I'm about to care extremely much about this molecules as graphs thing because I have a whole grand new theory of well, maybe it's a new theory of molecular dynamics. I mean, molecular biology. Here's the key insight, which might not be, oh, never mind. Well, you look at these reaction networks, which have dynamics. And I claim that there's information stored in the dynamics of the network that is different from the information stored in in concentrations of molecules. Anyway, different.
That's what our biochem library deals with from System Modeler.
Which aspect of it?
Pathway. I mean, it deals with modeling and quantitatively simulating pathways or reaction networks.
Oh, I should look at that. I had no idea we had that.
Yeah. It's called systems biology.
I know this field name, but you mean in our
but we've built a library. The System Modeler team built a library many years ago. It's free, that allows you to model those.
I remember that for some pharma, used by some pharma companies.
Exactly.
I hadn't internalized. I mean, how accurately does it model the reactions?
Very. The problem is how much data is available to,
Does the chemistry team know about this?
Yes, we've had that discussion. Actually, we've iterated between them and us. Yes, they do.
Okay. All right. Okay. Fine.
And these beautiful graphs that you see of reaction networks, they're usually just graphs. They don't have quantitative data. So the question is, how do you add the quantitative data so you can actually know reaction rates and so on, which matters?
Sure. Well, I mean, that's
but that's the same sort of type of other kinds of refinement of, let's say that you have a food web. Those are just structural, but there's actual rates there. There's sort of, cod eats herring at a certain rate.
Right. I mean, my claim is that there's actually another level of that, but anyway, let's not do
yes,
that.
let's not get. Let's move
on. Okay. Find vertex coloring. That's interesting. Okay, so if I do this and I say find vertex coloring of that. Oh, very nice. Cool. So, oh, that's very cool. I wonder when
Does
we're
it
gonna get
does
that.
does it work for non-planar graphs where it might have to give, you know,
Yes.
7 numbers? Oh, that's
Yes.
really cool. Okay.
Yes. Yeah. As opposed to maps, which are planar graphs, if you like, there's no bound. You know, think about the degree of a node of a vertex. There's like no way that you can get away with less than the degree number of colors.
Right. Is that surprising that it requires only is
Not
that
really.
surprising?
Not really, because they are bound, right? It's bounded by the size of the maximal click and the degree of vertices, right? So if you compute the vertex degree of your graph, you can pretty much guess already what's the upper bound and lower bound.
I see. Okay. But so if well, it's very cool. Okay, good. Chromatic polynomial, which we've had for a while. Why is
Yes.
what's the relationship between the chromatic polynomial and these chromatic numbers and so on?
So the chromatic polynomial essentially for each color give you the number of possible coloring for each. So for each value t, it gives the possible number of coloring essentially. So it's a count of possible number of coloring for your graph.
What's t?
So essentially t is the number of coloring you want. Right.
Okay, well, I should look at vertex coloring. So this will tell you this will tell you you can ask for multiple vertex colorings, right? So there are many, because there may be many vertex colorings.
No, there is essentially vertex coloring by one argument give you the minimal, so the smallest possible number of color you need to color your graph.
I see. So your claim is up to. I don't quite understand that. Is it the case that it's unique up to permuting the color labels?
No, I don't
No.
think so.
So this is just giving a particular vertex coloring. What if I want a different vertex coloring?
No. So what we are returning is in terms of size of the coloring, right? So there's a minimal amount which is invariant from the isomorphism. So if two graphs are isomorphic, right, because the neighborhood will pretty much match, so the coloring will match.
Well, but I think that there can be, I mean, can't there be two colorings of a graph that are not kind of, where there isn't a similar sort of automorphism or whatever? You know what I mean? Like, yeah.
Right, that's why we are returning integer 1, 2, 3. You could apply any kind of permutation of 1, 2, 3. That will
No, I understand that, but what Christopher is saying, and I'm saying as well, is that list there, is there more than one possible list, independent of the 1, 2, 3? So how do I get another possible vertex coloring that isn't just related by permuting the 1, 2, and 3?
No, they will be permuting they will be dependent. It will be permutation.
Okay, wait a minute. You're claiming that it's a theorem that basically the minimal coloring of a graph, there is only one way to minimally color a graph up to the labels of the colors. Is that correct? Clearly, if it's a non-minimal coloring, there are a gazillion ways to do it. Right? You understand the question?
No, I'm not sure I understand what you mean.
Okay, what I mean is this. Let's say I take this graph, okay? And I say that's the vertex coloring of that graph, right? Maybe an alternative vertex coloring is 1, 1, 1, 2, 3, whatever, right? In other words, something not related by permutation of the labels.
Yes.
Is that possible?
Yes, but when it's minimal, my claim is that you'll be pretty much a permutation.
No, but permutation on the labels.
Yes, on the labels.
Okay, but pretty much is not a theorem.
Well, because I will just essentially prove that there will be isomorphic. So, and isomorphic will be isomorphism on pretty much the label. right? When we talk about isomorphism, is on the label of the graph.
But it's not obvious to me, and there's either is a theorem or there isn't a theorem.
So I found that, I mean, there's a Wikipedia page for uniquely colorable graphs, which is talking about graphs which have the property that, I guess the weaker property that basically all colorings are just, there's only one coloring up to permutation of the colors. But
right, which is what we're talking about here. But you're saying the fact that there's a page about that means that there are many non-uniquely colorable graphs.
Potentially, although this is also talking about for K colors, right? So that's not necessarily, maybe in the minimal color case it's special, but I don't think it doesn't. I don't know. I'm sort of, yeah. It doesn't seem obvious that would be the case.
I think it should be checked. In other words, that there's no need to say find me another coloring. I also have the question: would it be useful to be able to say find a 5 coloring of this graph, or is that not useful, or is only the minimal coloring of use?
You get that.
That's the second argument. Yeah,
that's the second use case.
Find a coloring. Oh,
So
I see. Where those are the
6.
names of the colors.
Right.
Yeah.
You can give
red, green,
color
blue.
data such. Yeah, right. Pretty much.
Okay, so if I say this red, green, blue. And then I say, okay, fine. And now I say graph of %1, comma, vertex style, arrow %.
It won't work. We are fixing that. It's one of the new extension. So you have to thread, because we do the mapping from vertex, vertex name to color. But this is a feature we are going to add, so we can just take the list.
Okay. And you're going to add that for all the other vertex label and all that kind of stuff.
Yeah, where is possible. Yeah.
Okay. Okay. Cool. Yes, this is good. It's very nice. Okay. The question here, Ethan is saying, can you enumerate colorings? Well, that's what we're doing here. You can use the, okay. Okay. All right. That looks wonderful. Very nice. Okay, let's talk about planar graphs. Oh, do we actually get to answer questions like, I mean, given a planar graph, okay, first of all, how do I generate a random planar graph? Can I do that? Is there a random planar graph now?
No, not yet.
Presumably it would be a graph distribution also, right? Like you'd say random graph of blah, blah, blah.
Makes sense to me, guys.
It's not for 13, we think. So
isn't there an easy algorithm for generating random planar graphs?
Yes, you can do Delaunay mesh, but the point is you want a uniform distribution. I mean,
the big challenge, the big advantage of what we did with graph distributions is that we guarantee that we fill out the space correctly. It has the correct measures. So if you
I understand. I got it.
If we just want to sort of do a hacky function that generates some of them, that's easier.
Well, let's make sure there's at least one in the function repository for random planar graphs.
Right.
Because otherwise we're going to have a hard time. Sandra is saying just make a Voronoi of some points.
Yeah, so that's a hacky way to do
it.
Yeah.
I mean, I looked into this at one point. There was no like famous algorithm for doing it. Although there were, I think, a few papers, and it did seem like there were some ways to do it.
There's a Bosman sampler. It's doable. It's not complicated. It's a matter of, you will have it in 13.1. It's just a matter of sitting and doing it. So there's a clear technique for doing that.
So if I say, I mean, just to make one, just so that I can play with these functions, if I just say something like this, 10, comma, and then like 30,2. Okay, and now how do I get the graph from that?
Mesh connectivity graph.
Okay, planar graph, good. Okay, all right. So now Oh, that's useful. Planar face list. Let's see what that does.
Give it the name since you're going to play with it.
I don't understand why they're pairs there. Why aren't these faces?
The vertex names, you should say index graph of %14.
Yeah.
The vertex names that mesh connectivity graph gives are
Oh, I see.
Is the cell index.
Very nice. They're all triangles. Fancy that.
Probably except the outer boundary, which should be somewhere there.
I don't see an outer boundary.
I see
Oh,
it.
third line,
529. Yeah.
Yep.
Yeah, and that means the complement, right?
Yeah, it should be ordered counterclockwise, pretty much. Well,
So the orders are also. Sorry, go ahead. I mean, so you said that the orders are guaranteed to be clockwise and everything?
Yes, just in case you want to figure out what's the outer inner, what's the outer boundary. So it's counterclockwise, I think.
Nice.
Shouldn't the outer boundary be, shouldn't there be an option to drop the outer boundary?
I'm not sure you ever want to do that.
Well, but if you just want, why wouldn't you just want the interior pieces? Because you might be thinking it's a conceptually infinite graph. I don't know.
Well,
anybody else excited about dropping the outer boundary?
I haven't seen any use case.
All right,
like
fine.
that.
Forget it. Dual planar graph. Yes. Okay, fine. Well, that's very nice. Okay. Oh, the dual planar graph. I see. From a planar graph. So if I take this, I can say dual planar graph, and I should get a bunch of nodes I should have one big multi-legged creature. Huh. Okay, nice. Why did that come out with giant node size? Why did that come out with giant nodes? Charles?
Sorry, I don't understand what you mean by giant node.
Giant, as in this disk is big. Why is that so much bigger than this one here? See the size of that node there in the rendering?
Oh, I see. Oh, right. This right. Something strange is happening. Yeah, vertex size in the computation.
Something is setting vertex size?
Yeah, automation to actually determine the size of the vertex, right? So we need to compute a default value. So it's something is going wrong.
Okay,
not gone, but
what? Sorry, it is going wrong here, right?
Yes, it's not the best one.
Well, it seems wrong. I mean, it's just some mistake.
Well, it might be just something like that. This graph has fewer vertices in it or something.
We don't spend time actually looking at the position of the vertex, computing that. I mean, it will be costly. So
you're saying that this is simply, where do I put these? Help, where am I putting these? Put it in here. This is allowed.
So actually, just as a connected question, I mean, is there logic to the vertex coordinates here? Like, are they at the centers of the faces in the original graph or something like that?
Yes.
Cool.
Are we keeping that embedding, right, Charles? Are we changing?
Doesn't look right.
No, we're not keeping that embedding then.
No, because usually if you do that, which is the centroid of your face,
the
layout is really strange. I mean, it's all because like the outer boundary, right?
The outer boundary is going to be it's got to be a curve for that to work, right?
Right. So yes, we decided not to do that. There will be, maybe we can, do the vertex, vertex coordinate inheritance probably later on to do that.
Also, I think that there can be situations where if you just use the centers, the resulting straight line embedding, the edges might cross, right? But presumably you want, the dual is also planar, so you'd like to lay it out in a way that sort of shows it's planar.
Right. That's exactly what's happening here.
Okay.
This is running the planar layout.
Yep.
I recognize its footprint.
I really think you should look at why those dots came out too big. Just some issue. Okay.
Actually, sorry, does that mean there's a new planar layout thing as well? Because I know at least that the main old one was the one that's like shows up in a right triangle or something like that.
I mean, I think in version 12 also we have the turtle embedding, which kind of readjusts it a little bit. So it's that one by default.
Cool.
Okay. Yeah, this is a nice. Okay. All right. Let's go on here. Control flow graphs. By the way, in this thing here, what other things have I wanted to do with planar graphs? Yeah, I mean, the planar face list is definitely the thing I've wanted a zillion times. Is that enough? Is that anything else one usually wants to do with planar graphs?
Actually, sorry, how do these functions, like how does planar face list work if the embedding of the input graph is not like a straight line planar embedding? Does it just create its own embedding and then give you the faces, and all the guarantees about ordering and stuff like that are kind of out the window?
Right. So first is that, right, the embedding is not unique, right, for a planar graph.
Right.
Right. So what we do is, so if you provide us an embedding, and it is, we can check that the embedding is planar, we use it. If it's not planar, we use the default embedding.
Okay, makes sense.
Oh, I see. So this planar face list is relative to the default, is relative to the embedding that's given, or you should say that here.
Yes, we'll do that.
And you should also say what the clockwiseness guarantees are. Does that make sense?
Yes.
Okay. Dominator tree graph. What the heck is that? And obviously we've got a spelling word there. Did you report the spelling word, by the way?
Not yet.
What is a dominator tree graph?
Oh, I guess my update didn't make it.
Okay, how does this relate to like transitive reductions and things?
So essentially the dominator vertex, it's essentially the vertex, the unique vertex, such that any path goes through that vertex to reach, a specific set. So so that's pretty much it. So you have.
So it's like a treeification of the graph. It's like that has to be the root of some. To get to a given vertex, you have to go through this one.
Exactly.
By the way, I see a comment on the live stream from Ethan about add a unit distance graph queue or find unit distance embedding.
Yes, that has been a request from several people. We'll do that at some point, where essentially they want the length of.
Oh yeah, I've wanted that. I've really wanted that. I had code to do that like 10 years ago. Maybe you helped me with that, Charles. Maybe it was 20 years ago. I don't know. 10 years ago, perhaps. I don't know.
Yes.
No, it must have been more than that. I don't know. Anyway, who knows? But I mean that should be a graph layout, right?
Yes.
Yeah, it will be very useful. Ethan is complaining about vertex label collision avoidance, which I know we
will do a future focus on more advanced label layouts.
In the earlier release, we already did some improvements.
We did, yes. So if Nathan and others didn't notice it, with all these, like when you do like a complete graph with labels, it use intelligent label placements, or grid graph, etc. Those guys use have optimized label placements.
Right. Sandra's asking, is dual planar graph of dual planar graph the identity operation?
No, because it's going to, when you do the dual planar graph, it's going to make this new embedding, right?
Yes.
I mean, certainly the embedding of the graph you get back will be different, but probably it'll be.
But the graph itself is isomorphic, is it not? Let's find
It's
out.
definitely isomorphic, but I mean, it might be if you do 3 dual planar graphs and then 4 and then 5, then it might just start going back and forth because it's just the same graph being fed to the thing that's generating a planar embedding, right?
Well, here, let's just do it just for fun. So we're just saying this GGG, let's say 10 steps. Hey, this is taking a while. Why is this taking so long? Help, why is it taking so long? Charles, it's not a very big graph. Why is it taking so long?
Well, because, I mean, that's the cost of computing vertex coordinate and validating. But it's taking a little bit too long. So we'll check on that, not sure.
Let's just try a smaller one.
So I bet if you say face list, like if you did dual planar graph of dual planar graph, and then you look at the face list, you'll probably get the same face list as if you just ran face list of GGG, right?
Yeah, you should do, shouldn't you? Well, actually, it's not obvious that you would.
Yeah,
right?
it's
Because there
not
might be a
obvious, but I
different
think
embedding.
you will. Yeah.
There. This is labor saving or not. Let's see. Planar face list. Oh, for goodness sake. Oh, I didn't make index graphs out of them. Okay, who knows the precedence of, is that going to work or do I need parentheses?
No, you don't need parentheses.
Well, the theorem is not true. Doesn't look like it's true, at least. Okay, well, so that isn't in fact the case. Okay, let's keep going. Okay, so now this dominator tree graph. What should we look at there? I mean, wait a minute, let me look at that.
So first, the immediate dominator list gives you the immediate dominator of each vertex, right? And then the dominator tree graph actually just gives you the actual tree, which represents that.
So that has to be with respect to a particular vertex.
Yes. No. It's probably because this graph is on. Oh, it's wider. It just work on directed graph.
Oh. Okay. So if I say, how do I make this a directed graph? Let me just say, what happens?
Directed graph.
Yeah, directed graph.
Well, you will put the edge on both sides, I guess.
Oh, that's boring because it's just that. And then if I said simple graph, would simple graph, what will it do? Well, no, it'll be confused. I don't know. Give me a nice way to make a simple, make a
just do random graph directed edge 0 true.
Okay.
I think you should actually even remove the second argument. You should give you the full list in principle. No.
How many arguments does it think it needs?
No, it needs the vertex.
Okay.
Well, we should probably do the one argument form to just give you the.
What would the
List
one
of
argument
lists.
form do? It would give a list of lists.
Yes, for all of them.
What does that mean? What does that list that I just got out mean? That means for each, I don't understand. What does that list
No,
mean?
no, no.
Immediate dominators of the directional graph from the root vertex V.
Right.
So I
So-
see this is the things which are the predecessors.
Yes.
That's a very weird name, this immediate dominator thing. Is it basically the reversal of, I don't understand. What if there are two feeders into a given vertex? What is the dominator in that case? This is what feeds into a given vertex, true or not true?
When you say feed, yeah, it's in vertex, right? I mean, it's what you mean.
Yes.
So, right.
But it's the vertex in component. If I look at the vertex in component in %27, I say vertex in component of %27, comma 2, for example. Yeah, I get 4 there, right? This is the thing that feeds in, right?
Right.
If I say the in component of 3, I'll see that the immediate in thing will be, okay, now I'm confused. Why is there a 17 there? Why is the 17, the in component here, okay, vertex in graph, is that what it's called? No, what's it called?
Vertex graph component. Vertex in graph component.
In graph component. No? Wait a minute. What is it called? Vertex. What do you say?
Oh,
Vertex.
yes. Well, myself, I don't remember the name now. It's
Doesn't it end with graph? I'm pretty sure it ends with graph.
Yes, it
Yes.
must do.
And it should
Help.
be point.
Vertex in. Well, this should have that name.
Yeah.
so
It
it's
should.
vertex in component graph, right?
Okay, but why isn't it listed on the in component? Why isn't it listed on vertex?
It should be. It should be.
Yeah.
Okay. Bluff. Okay, let's see if I say, I just say to level 2, for example, level 3. Okay, so this is saying going into 3 here, why is 17? I am totally confused. Why is 17 the immediate dominator of 3? Why isn't it 34? I don't even understand how 17 even gets there. Right, 17 has to go through 4 steps to get there. Okay, anyway, there's some issue with this.
Can we?
Right,
I mean, can we return to this one next time, and our documentation will be kind of.
The clear example, the clear example are in the documentation. I'm not sure I kind of trace down what's happening here, especially that you have on directed edge, right? Different direction, which can affect the.
Right, we'll pick it up again. Okay. Okay. Oh, that's cool. Graph objects from binary tree. Okay. Oh, that's cool too. Works on tree expressions. Okay, so if I say random tree of 50, for example, then what you're saying is if I say find shortest path of that random tree, %34, from let's say 10 to 26. What? That doesn't look right. Look, there's 10. There's wherever it was, 26 was somewhere here. There. Why doesn't it do it?
But what is the name of your? So when you do the random tree, what's the vertex list?
Yeah.
I'm not too familiar with the vertex. Right.
Splafferoo. That's a bit confusing. So
But it's
if I were
because
to
you
do,
can have the same label appearing in multiple places in trees. It's one of the main
oh, that's
points,
right. That's one feature of a tree.
So I think it's the label, comma, and then the position here, right?
No, we don't handle pattern in the find shortest path.
Okay, so if I pick, I mean, basically, to get a path, it's also very weird, if I might say so, that the vertex list is not sorted in order of the tree ordering, in some kind of lexicographic tree ordering.
It might be in the reverse tree ordering, because I think 34 is the root.
Yeah, but it's not,
Yeah,
because where's
it is.
1, 1? Why is 1, 1 not appearing?
I think it's
high up?
depth first.
Oh, gosh. Well, that's interesting in its own right, because I'm about to do this giant study of traversal orders.
Okay, we have a big thing coming up in our tree review of traversal orders.
Oh, really? Okay,
Yes.
Great.
Yeah,
Okay, well,
there's
anyway,
a
so
whole big
that's going to be
subsystem
relevant.
for that.
Okay, really? When are we doing that review? Because I want to see that.
I don't know. It should already be scheduled. I just don't. It's like a big blur of design reviews coming up.
Okay.
I've
Is it a
ordered it.
traversal order option or what?
Yes.
Oh, that's what we discussed. Great. Oh, I want to see that. Okay. Okay, so vertex list will probably have a traversal order then for trees, at least. But okay, so this is just going to give me, in the end, if I, what's that?
Why vertex list should have a traversal order?
Yeah, it's a
No.
thing for tree expressions only.
Just,
You know, vertex list is a thing for graph.
and plus,
Well, but
traversal
for
order
any
is,
of these, presumably though, like if you say graph of a tree, right? If you're converting a tree to a graph, you want to be able to specify the traversal order that you're using, and then maybe functions like vertex list that automatically do this maybe should also take that option.
no, this framework is a general framework for graph. We shouldn't have specific option for trees. I think that's the first thing. Second, also we respect actually. I think there is the new function in tree. We call it what, graph tree or tree graph, which from the tree you generate a graph. So essentially we respect that structure on the vertex
Tree graph.
list.
That's what it's called.
Right.
Tree graph.
Tree graph.
Okay. There
Oh,
we
right.
go.
It's the old one. Right.
That's cool. That's really cool. Okay. Okay. I mean, it's sort of unfortunate, and this is something for the trees group, and we should probably bring this up in that trees review, that you can't get something where it ignores the names and just tells you the part numbers, which it after all knows for a tree. You see what I'm saying?
I mean, you'd say shortest path from, and then you give it 2 part numbers.
Yes. I think that will be useful for a tree. Can we bring that up in the trees review, please?
I mean, it sounds like something that should be an option for tree graph, but yeah.
It should be in tree graph, and it cannot, I mean, the general framework, the way we actually is built,
okay,
shouldn't be dependent on that. Right?
Okay, so tree graph there. And so now what's the vertex list of this? Okay, that's the same thing.
Right.
I'm confused. Let's bring this
It's
up
just
in the trees.
all the functions that are graph functions that take trees, they just call tree graph before they process them.
Yes. Okay.
Conceptually, pretty much, yeah.
Yeah.
Okay.
But I think it might make some sense though for them to also take tree graph options, if there are significant tree graph options. That's a different issue.
I don't think he should.
Charles is pushing back on that, but I'm not sure he's correct about that. But he doesn't want vertex list, which is a general graph function, to take things specific to trees.
Right. Find shortest to.
Should it take things specific to molecules too? Should it take things specific to
for data structure? Whatever we decide.
Well, so maybe then we need options in tree graph to do the appropriate stripping or something.
Yep. So that's why it was the specific constructor. I believe it was added, and we overload the function for that.
By the way, when are we going to have DAGs? That's just a question. I mean, now that we've got trees, maybe it's time to do DAGs. Let's see. Okay, so let me see these ones for data structure. That seems cool as well.
They're not yet in the prototype build, so.
Okay, all right, okay, fine. But that's an extractor. If you give it a data structure, like if I give it a linked list and I say graph of that, will it give me just a chain?
No, we stick on the data structure, which explicitly graph based. But yes, we can do that for linked list, but we stick for binary tree and AVS tree and so.
Yeah, okay, fine. Okay. Are there any graph functions that you might have thought will work for trees that don't? Like, for example, well, graph plot. Oh, I see. You can give a different embedding if you want to. That is a very untree-like embedding. By the way, when are we getting hyperbolic embedding?
Oh, well, there's still some work to actually polish. We have the layout, but there's still some performance issue and improvement.
Because that's obviously very relevant to the trees people.
Not 13.
Okay.
Oh.
Okay, fine. But I've got a question, which is
this is if you look at the list of things, it's very overloaded right now. We can't, you know.
I'm not pushing, Roger. I'm just asking.
It's coming.
Question.
No, it's coming. It's in the pipeline.
Okay, but I'm making a design point, which is that in the trees framework, you might want hyperbolic layout of a tree. And is there a way to? Is there a graph layout option to tree? Does anybody know?
Yeah, they've pretty much added all the relevant graph options by now. That's one of the new things.
Do they look like trees or like graphs though? If you ask, you know, you use graph layout, like are the labels green?
Well, I mean,
you have to be in that review. Let's deal with that in that.
Yeah, okay, fine. That's a different thing.
Yeah, it's a different review.
Okay. Well, actually, we can answer that question. Give me a layout, circular layout or something.
Let's do it in that. I don't know if it's in proto. Let's.
Okay, fine. Just so long. Is somebody taking notes here? Can you make sure to have this? Who's taking notes here?
Yeah, I'm taking notes.
Okay. Scott here as well?
Yep, hiding in the back.
Okay. All right. So can you make a note of that, please? Make sure it's in the trees review. Okay, that's details of how we're doing builds, right? Isn't that a new library? Were we using that one before?
Yes, we were.
Okay.
No.
Right. Okay. Let me look at some comments on the live stream before we move to geometry. Let's see. If you remember. Okay, if you permute the order of, there's a question from Sander. If you permute the order of vertices, does it always give the same coloring? I would say the answer is probably no. Am I making sense? Here, if we permute the vertices in here, the names of the vertices, do we always get the same coloring? That's the question.
No,
that's the theorem we don't know, basically. We should answer that question, and we should say it in the documentation, whatever is true.
No, we guarantee what I say. We guarantee the minimality, but we cannot guarantee that it's exactly the same coloring.
Okay,
so the result there, if you do a max, it always will be 3.
No, I get it. I get it. Okay, so we should just say that it's not a unique coloring. So long as we say that, it's all good, right? And if there's a condition where it is the unique coloring, who knows what it is, that's stateable, we should state it. Does that make sense?
Okay, we can try. I don't see how useful it is. That's my
no. The reason I'm saying this is, look, you know, let's say you are trying to do any one of these things, register allocation. Okay, let's say that there's an additional constraint on your registers. Which ones are nearby? Which ones have have crosstalk between them, or who knows what else, right? And you say, that's nice, that's a register allocation coloring, but what about another one? right? Is there another one? Is there one which will where some other constraint will work better? I'm making sense.
Yes.
And so,
I mean, it's also maybe
But
just
then
as a general.
But then that's a completely different problem you are solving. That should be a completely different function. It's kind of what I mean. Here, there is a specific goal, something simple we are computing.
well, I know it's like find path versus find shortest path.
Exactly. Yep.
Right. I'm just asking you. The first question is there a theorem that says there is only, that shortest path equals path? And we're saying is probably not.
No.
Okay, fine. So then there is a question of multiple vertex colorings and how one might compute those and are they worth computing? Right? So we just state in the documentation, it's not a unique vertex coloring.
Well, there's maybe also the question of, let me see, I think we're a little inconsistent with the find functions, but like, for example, with find path, find shortest path, or like with find graph isomorphism, even in the one argument case, find graph isomorphism returns a list of a single isomorphism, right? So like maybe if this function in the future were, took a second argument if it had some arguments where you could give back multiple, colorings, then it would
right. We may regret the fact that it's doing one level list.
Well, here the second argument, there's a case where, it's not easy to find the coloring, but you don't want the minimal coloring, right? Let's suppose you just want to, give a really large vertex, which if you want the minimal will take 20 days, but you just say, I want, a coloring with, 10 color. So that's the goal of the second argument. And then we can find it really fast and we give it to you.
I think the question is just like, if in the future, the point is just if similar functions return.
It should be a different function because I say the goal are different, right?
Right. But if it's a different function, then maybe this function should have a different name because this does sound like the name of the function. If there was a function that returns many things, this would probably be its name.
What does find shortest path do? Doesn't it just return one thing? Yes, it does. Find shortest path like this is a one thing. Whereas find path is not. Well, but you're basically saying you don't think it's super important to find multiple vertex colorings. And so if we end up with another function.
It's also not super clear. There's a bunch of things about does it show you only the colorings that are unique up to permutation of the colors or, et cetera?
There is all variety of coloring we can do, all game we can do in coloring. Here we are fixing, there is a standard way, standard request and standard application of coloring, right? And is what is solving. So we may decide to change the name of the function, that's fine. But, generalizing it to all coloring problem, that's not realistic.
Okay.
Yeah, absolutely. Right. I'm just wondering if maybe if there's some word that could be inserted into its name that would, sort of future proof.
And we're using coloring for historical purposes. It's sort of a stupid name because it's really finding finite number of assignments, right?
Or labels for vertices.
Yeah.
Right. So
I think it's called coloring.
I know it is,
yeah.
But it's sort of stupid, right? Because there are infinitely many colors. There is not just finitely many colors in the world.
Right.
I assume it doesn't make sense to call it a find minimal coloring because with the second argument, you might ask for a coloring that's not.
This is what people, when you talk about graph coloring, this is what people are looking for.
I think this is going to be okay. Okay. There's a question about editing the positions of the vertices. Whatever happened to that separate application that could do that?
What?
We had that weird Java thing for a while that did that. Being able to edit the vertex positions.
Right. There is a how to coming soon, which we just show you can just use locator, right? So that's one easy way, right? The other way you can convert it to a graphic and then use the graphic editor.
But then you can't get back. So wait a minute. So you're saying we have something coming, which is an editor. Is that true?
No, we are just writing a how-to, just to show people how you can just use locator. So you can, set up the vertex function or vertex shape with locator, and then you can move it inside the graph.
Yeah. That's awful. I mean, we should have a separate discussion about this because there's some other places in geometry and other things where we're starting to have more of this kind of editing. And with molecules, we have an editor, obviously. Right? We have molecule draw. Right? Can we, okay, separate meeting discussion. Scott, can you please put it on the list?
Yep.
It won't be in the current cycle. Let's see. What are molecular grids? I don't know what a molecular grid is. Nick is asking if it's using the embedding, does dual graph place vertices in the centroid of a face?
No.
The answer is no. But could you ask it to do that?
Yes, so it's something we are considering in terms of inheritance. So I don't think we implemented yet. We can say vertex coordinate goes to inherited, so we can inherit it from the original graph.
Okay.
So
Okay,
that's
fine.
a possibility.
That sounds like a good idea. Richard says dominator trees are very useful in compilation. Apparently, LLVM has a class dedicated to them. It's interesting.
Yes.
Yes.
The suggestion came from Tom.
Tom, yep.
And what is it? What is it used for in compilation?
There's a number of I can't remember now. Actually, it's better that Tom says. But it's one of these very base.
But it's for the single assignment form, right? When you want to.
Oh, I see. Right. Right. I think my friend Greg Chatham was the person who pointed out that register allocation is equivalent to graph coloring. I think that was one of his heroic moments at IBM. Let's see. Bob is wondering whether dual planar graph takes more than linear time. We don't know. There was something fishy about what was going on there. Will code involving graph be compilable in 13? That's a Christopher question. I don't know if there's anything to say about that yet. Is there?
I mean, not in 13. I mean, this is irrelevant to this meeting, but I was playing around with basically writing type signatures for graph functions, just as sort of a test of the compiler, though not for graphs. But I don't think it's going to make it in.
Fair enough.
And also those functions, pretty much all call the evaluator, so it doesn't help you very much.
Well, it does help you when it has wrapping around it that is compiler, compilable wrapping, and the graph functionality itself is pretty efficient, I think.
Yeah.
Crucial made the comment, says they've made a package for dendriform algebra. It's a strange and different algebra. Okay, I don't know about that. Some kind of tree-related algebra. Sounds interesting. Okay, question. Sandra is saying, look at maps of Europe. Are they colored the same? That's an interesting question. In other words, this whole question we've been addressing here, presumably it is the case that there is no unique forecoloring of the map of Europe. It's not self-evident that would be which of those things would be the case.
Well, one of the horrible secrets of maps is that the actual map of country borders is not planar because there are islands and there are exclaves and lots of crazy stuff.
I'm going to have to run. Well, obviously, we're going to schedule at least 1 more hour meeting.
Hold on, I just want to see some of these other comments here, and then we can. I'm going to go find clicks, which can enumerate. Oh, find coloring instance. Sander suggests. Find vertex coloring instance. Is that better? I don't think it's particularly better because, like, find shortest path, there might be more than one. Dan is suggesting graph setter, which is the future. That's a decent name and concept for this thing that you're describing with locators. Dynamic graph plot. Yeah, that will be lovely. Edmund is saying dynamic graph plot that uses locators behind the scenes. Okay, Richard is saying dominator and post-dominator trees. I don't know what a post-dominator tree is. It sounds like it's probably the reversal of a dominator tree, perhaps.
Yes.
Core tools used in numerous analyses and transformations that allow us to reason about the order of execution of basic blocks and instructions. Used to compute the dominance frontier, determining the optimal placement of phi nodes, confirm safety of many transformations like instruction syncing and hoisting. That's interesting. Sounds cool. That's interesting. Actually, that whole business, that whole thing you're mentioning is relevant to things I'm thinking about which amount to traversal orders. Let's see. Okay, Nick is commenting for graphics. Dragging is possible, but resizing is not possible currently with locators and so on. That's an interesting comment. That would certainly be useful. Okay, we got a bunch of exciting stuff coming here for geometry, but it sounds like we're not going to be able to get to that. Oh, this is really exciting stuff. Oh, very exciting stuff. Really? Have you managed to get this to actually work now? The 3D constructive solid geometry?
Yes.
Wowee. It's been 12 years or something, hasn't it?
It's going to be exciting. So, okay, let's look at it.
All right. Cliffhanger.
Yes.
Cliffhanger. Okay, all right. I just want to see what.
Oh, there's many more. This is just things that we moved out that were on our initial target list. We have a much, much longer target list future. Much.
Okay. Well, this is wonderful stuff. All right, we should probably wrap for now. And look forward to the next one of these, hopefully scheduled soon.
Okay.
And thanks to folks on the live stream. Good suggestions and comments, much appreciated.